Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We're at lecture 5.4, the main performance considerations of atomic operations. The objective of this lecture is for you to learn the main performance considerations of atomic operations. Atomic operations have a unique property where the latency of the operation actually translates into the throughput of these operations. And we also will go into how you can do atomic operations on global memory and how some of the more recent hardware allows you to automatically perform shared atomic operation on shared L2 cache, even though you think you're doing atomic operation on the global memory. And then how we can actually perform atomic operation on shared memory variables. So here is a simplified diagram about how the hardware performs atomic operation in a GPU. So we have the streaming multiprocessors on top here, and we have the DRAM system on the bottom. And each atomic operation starts with a read operation, and this is a memory read, and we're showing this operation in terms of an arrow going towards the streaming multiprocessor. And this operation has a latency of hundreds of clock cycles. And then we will do the quick calculation, such as a add, and then we will write the result into the DRAM system, and therefore the atomic operation will end with a write operation, which also has a latency of a few hundred cycles. So during this whole period, there's no other access that can be done to the location that the particular location that the atomic operation is operating on. So if we look at a atomic operation timing on the DRAM, if we in this picture we show that the time goes from left to right, and we show two atomic operations that operate on the same memory location. So here we show atomic operation n and atomic operation n plus 1. And these could be atomic operations performed by different threads in a thread block, or it could be performed by different threads in different thread blocks. So for each atomic operation, we show a breakdown of timing on top. Essentially, we will have the DRAM core access delay that we have already described in one of the previous lectures, and we have a little bit of a delay for transferring the data from the DRAM output buffer to the streaming to the GPU, and then there's an internal routing delay from the boundary of the GPU chip into the streaming multiprocessor. And then we do a little bit of a calculation, which is that addition, and then we need to send the data out for that store, and then it needs to go through the routing network of the chip to the boundary, and then it will be transmitted from the chip to the DRAM, and then you will need to write into the DRAM core array. So that will again be a DRAM delay. So we will have the same timing for the next atomic operation. Notice that these two operations cannot overlap because that's exactly how the atomic operation eliminates the race condition errors that we can have in those read, modify, write operations. So whenever we have a load modify store access to the same memory location, we have two full memory access delay for each one, and then all these accesses are also fully serialized, and all the delays are exposed in terms of the access timing as far as the application program is concerned. So because of this behavior, we have a unique situation where latency actually determines throughput in a parallel processing system. Usually, when we have a massively parallel system, we have we try to optimize throughput more than latency. And this is exactly how the GPUs are designed to work. Even though individual operations can take a long time, because we have massive number of threads, because we have all these zero cycle latency scheduling, we can achieve very high throughput of executing these operations, even though the latency for executing each individual thread's operation can be very long. However, because of the exclusive nature of atomic operation, if a massive number of threads access the same memory location with atomic operations, they are all serialized. And if you look at the picture, the rate at which these atomic operations can be performed on the same memory location is indeed limited by the total latency of that operation. So the inverse of the total latency actually is the throughput. And this makes the parallel processing using atomic operations extremely dangerous, because we can, if we're not careful, we can accidentally serialize all the threads and essentially expose the full latency of the memory system to all the threads. So if we look at the practical implication, each memory access has hundreds of clock cycles. So that the two read and modify write, sort of the two memory access latencies, the read latency and the write latency together, is oftentimes more than 1,000 clock cycles. So this means that if many threads attempt to do atomic operation on the same memory location, then we could actually reduce the effective memory bandwidth by over 1,000 times. And this is a very, very dangerous situation. And so we need to be very careful about any of these potential accesses to the atomic operations to the same memory location by a large number of threads. So you may have a very similar experience in a supermarket kind of environment. So some of these supermarket customers realize that they missed an item after they started to check out. So, let's say they're in line, and then when they reach the beginning of the line, when they start to have the clerk to check out the items, they say, "Oh, I forgot to pick up that juice that I'm supposed to buy." So the customer will run to the juice aisle and then pick up a juice. Meanwhile, everyone else in the line will be waiting, and the clerk may have already finished checking out all the items on the conveyor belt. So that latency that the customer has to go to the aisle and come back is fully exposed to all the other customers that are waiting in the line. And so this can be very annoying for you and for everyone else waiting in that line. So imagine if we have a store where every customer wait in line. When they come into the store, they wait in line in the checkout. And then as soon as they get to the top of the line, and then they say, "Oh, okay, I'm going to begin to shop." So that customer will go to the entire store, do that shopping, and then come back one item at a time to finish his shopping, while everyone else wait in the line. And then the second customer, when the second customer reaches the beginning of the line, they will do the same thing. The person will begin to shop, and this will be a terrible, terrible system, because the rate at which the checkout can be done is 1 over the entire shopping time of a customer, a typical customer. So the entire shopping time latency determines the rate at which you can check out the customers. And this would be a nightmare for the supermarket. So, but whenever we have atomic operations to the same global memory, we actually have a very similar arrangement. So this is the reason why I wanted to use this example to give you that intuition. This is one of the most important intuitions that you need to have for programming parallel systems. Because the latency gets translated into throughput, and therefore translate into the application visible productivity or performance. There has been a lot of hardware improvements that are done to improve the latency or shorten the latency of atomic operations. So starting with the Fermi GPU and then the Kepler GPU, the later Kepler GPU, the atomic operations can be performed in the L2 cache or shared L2 cache across, in the GPU. So in Fermi, NVIDIA introduced a level 2 cache that is shared among all the streaming multiprocessors. So this actually provides a very interesting opportunity because all the accesses to the global memory from all the streaming multiprocessors goes through the same L2 cache. So if we need to do atomic operation on the global memory, we can actually just perform the operation on the L2 cache, and that the atomic operation to be performed by one streaming multiprocessor will be visible to the other streaming multiprocessors because they all share that L2 cache. So this allows the GPU hardware to perform all the atomic operations at much lower latency because now you no longer need to do the data transfer to the DRAM and suffer from that DRAM core delay in both the read and write accesses. All you have to do is to go to the L2 cache, do that read from the L2 cache and write to the L2 cache. So this is illustrated with this tiny example where the access delay of the L2 cache storage is much shorter. So this is shown as a shorter white sections. And then the data transfer from L2 cache into the processor still need to go through the internal routing network, but it's typically also a little bit shorter. And then you would still need to write out. So overall, the latency is much shorter because essentially the core access, DRAM core access delay has been translated into the L2 cache data storage access delay, which is orders at least an order of magnitude shorter. So this allows each atomic operation to be performed at a much lower latency, and 1 over that latency becomes the throughput. So the throughput is improved dramatically when you use L2 cache. And the best part is that the programmer will still think that they're using the atomic operation intrinsic on the global memory. However, because the cache, L2 cache, automatically caches the data from the global memory, so the atomic operations are actually transparently performed in the L2 cache. Therefore, all the improvements are transparent or free to the programmers. There's another hardware improvement that has been in place even before the Fermi generation. That is, we can perform the atomic operations on the shared memory. So the shared memory is extremely fast, much faster than the L2 cache. So by providing a pointer into a shared memory location, what we call the atomic operation, we can perform a very fast atomic operation. So mainly because the access to the shared memory is of very short latency. And so 1 over that latency is going to give us the throughput. However, all the threads still need to be serialized. So we will still have the exposed latency. It's just that the latency got even shorter. So this is shown by a much shorter internal routing latency and even shorter the storage access delay. So the main limitation of the shared memory atomic operation approach is that shared memory is private to each thread block. So only the threads in the same block can operate on that same atomic operation in the shared, if we put the variables in the shared memory. So we need to have do the algorithm work called privatization, and this is going to be the topic of the next lecture. So by now you have understood all the main performance considerations. the most important point is that for atomic operations that access the same memory location, the latency, the full latency of the atomic operation is translated into the throughput. 1 over that latency is the throughput of the atomic operation. And therefore, we have several hardware mechanisms, such as the L2 cache atomic operation, such as the shared memory atomic operation, to drastically reduce the latency from that global memory atomic operation. So in next lecture, we're going to put it together and show you how we can use all these hardware improvements to achieve much better execution throughput or performance for the histogram kernel. Thank you.